Hello, welcome to the next discussion in the real-time systems module. What we're going to talk about today are interrupts. Now, one thing we have to consider is what is the structure, the overall structure, the glue that holds all our functions together in a real-time system. The first thought most people might have is you need an operating system. But in fact, as I will show you later, the structures of a traditional real-time operating system is not practical for factory or plant or vehicle automation. The reason is that when an event happens in the real world, it's no good just scheduling it to happen. It may be very important. It needs to happen now. We can think of lots of examples. You're driving along in your car and you press the brake pedal. You don't want that action simply to be scheduled into a real-time operating system, to be queued, to wait. You want the car to stop. You want the car to stop as quickly as possible. What if we're running a conveyor belt, and on that conveyor belt something is moving along through a process, perhaps it's being sprayed with paint, or wrapped in some film, or put in a box, and it reaches the end of the conveyor belt when a crane has to come down, pick up those goods and move it over. That is usually achieved with a mechanical component called a limit switch. A limit switch. And all that a limit switch is just a simple contact closure. As the box moves along, it hits the contact and it closes a switch. That sends a signal back to our real-time system to say the box has moved from A to B. Now we have to bring the crane down, or push it on, or spray a different colour around it. That box, that signal, must be acted on now. If it's not acted on now, it will just carry on moving and fall on the floor. We can't have that happening, can we? So events in the real world are more often than not events that can be scheduled to happen, but must be acted on immediately. Now let's go to our basic input signals. We know from Nyquist's theorem that if we're going to reconstruct a digitally sampled signal, we must take regular samples at high speed. It's no good taking a sample here, here, and then there. They must be regular timed intervals. Otherwise, there's no way our computer can reconstruct the analog signal that was created by that sample data system. So precise timing, events happening, must occur. We can't use an operating system for that. We have to have another mechanism. That mechanism is called an interrupt. Now what is an interrupt? In general, it is a mechanism, it's a software entity, it's a way that a task, a function, signals to the processor, hey! I'm important. I am more important than what you are doing now. Whatever you're doing, you must stop. Stop all functions, all processing. I'm the boss. I'm the interrupt. You service me now. That's an interrupt. An interrupt is pressing the brake pedal. So you stop running everything else in the car and you immediately service the request from the driver to stop the car. Quite lots of things. Reduce the fuel, start applying the brakes, whatever. There's a number of functions that must be done immediately. We could be perhaps baking some ceramics in an oven and there's a precise cure time for the glaze on it. Now if you overrun that, you'll get the wrong colour on the product and so you won't be able to sell it. So when the timer times out and says, right, you've had your 15 minutes cure time, now switch the oven off, you've got to switch it off now. So never mind the computer's doing something somewhere else, it must stop what it's doing and take care of the important event. That is an interrupt. An interrupt is a software function. It's totally asynchronous. You don't know when it's going to happen. You can't plan for it. You can't schedule it. It is an event in the outside world that signals to your computer, I'm important, you must stop what you're doing, you must now take care of me and not your other process. So anything you've ever learned about good software design, nice structures, nice flows, hierarchical approach, knowing where you're going to in your program, knowing where you're coming from, nice data structures, forget it. Well, don't forget it, but in terms of interrupts, you can't do anything about it, because no matter how lovely your program flow is, at any time somebody else can come along and say, "Oi, stop!" And you've got to stop whatever you're doing and service this external event. And you have to do it in a manner that doesn't disrupt your original program. So you have to have a clean break. You have to be running your program, stop, cleanly, exit, execute the interrupt, get it out of the way. It's an irritant, it's causing us problems. Do what it wants to do, and then return to the main body of our program as if nothing had happened. It must be totally transparent. The main body of our program must have no knowledge that it was momentarily paused while our processor ceased what it was doing and did something else. And what are we trying to do? Well, we're trying to recreate a real-world environment. In the real world, things happen in parallel. You have parallel processing. Computers can only do one thing at a time. No matter how clever they are not parallel processors. They can only execute one line of program code at a time. So we have to create structures that mimic parallel processing, the real world processing, but in a single thread. The traditional way is through multitasking, multi-user operating systems. I'll discuss those later. We can't use those to handle things that have to happen now. Instead, we use interrupts. Now, let's go to the basic concept of an interrupt. What types of interrupt can we get? Well, the commonest type of interrupt is an external event. Let's consider some of these possibilities. What could be creating these interrupts? Let's start by, here's our processor, our microcontroller, lots of little pins. This is the I/O and the power supply. Here is our microcomputer, and there it is. It's running a nice sequential program. Maybe there's a branch in it, but we know where we're going. We know where we come back to. Good program design, and so we continue. So we always know where we are in our program. That would be an ideal program. Perhaps it would then loop round and start again. If it was a real-time system, it's probably going to be some sort of cyclical program. How about the outside world event? Well, a typical example is, here's a switch, and in fact, this is my brake pedal. So when I close my brake pedal, that sends a signal to the computer to say, stop! I am braking. I am the driver. I've pushed my pedal down. I want the car to stop. And that is translated into, in the picture, a very simple digital signal. By closing the switch, logic level 0 rises to logic level 1. Now, I've said that could be a brake, or the other example I gave was a limit switch, or it could be a timer. Whatever the cause of the event, something has finally signaled a binary signal to our computer. It says, I was off, but now I am on now. So it's a rising edge event. It's a rising signal. And what happens in binary terms is that that signal went from a low to a high with a rising edge. And that instance, that is the instance of the actual interrupt. That's how it's occurred. Whatever the source was, there are many different ways and sources of different types of interrupt. It will be signaled to the computer by a rising edge signal. Now, all microcomputers, all decent computers, in fact even a Pentium has one of these things, there is a single pin on a processor called the interrupt pin. So even though we may have lots of other facilities in here, one of the pins on the processor is designated the interrupt, INT, the interrupt pin. And the way it works is that when that signal sees the rising edge, the processor is instructed to stop what it's doing and it goes off to service another routine that exists somewhere else related to that event. Now I'll show you how those work in a minute, but let's discuss how they work, or how the hardware works. The interrupt pin can be set to be rising edge sensitive, or it may be falling edge sensitive, or it may be level sensitive. That is, whenever it's high, it issues an interrupt, or whenever it's low. These are the 4 different types of external interrupt you can get, and this is the generic name for them all. External interrupt. I'm not going to spell out interrupt in full every time, you can get it out of the book. An external interrupt is a pin on the processor, and all processors have an interrupt pin. It's essential. Microcontrollers usually have lots of different ones. A Pentium, which isn't very good at real-time systems, it's just got one, but that's used to generate the internal timing, the real-time clock that drives the Windows operating system, and we'll talk about that later as well. All processors have an external interrupt pin to allow the ability for some external thing outside of the computer environment to interrupt us and say, "Oi, stop what you're doing, look at me." When you initialize your system, you have to instruct that pin to issue the interrupt on either the rising edge or the falling edge, and that's an edge sensitive detection. Or it could be a level sensitive detection whenever it's high or whenever it's low. Now in practice, level sensitivity is not good practice. The problem is that all the time that is present, it's signaling the interrupt. So once you service the interrupt, you have to ensure the level goes away. Otherwise you will just end up with a re-entrant code just processing the interrupt continuously for the whole of the level. But it is there for historic purposes. That is the way it used to be done many years ago. So an external interrupt, a summary, it issues the interrupt on either the rising edge, the falling edge, level sensitive high, or level sensitive low. Those are the 4 types of external interrupt you can get. What other types of interrupt are there that might be useful? Well, the external interrupt is one that monitors an outside event. You don't know when it's going to happen. But the other thing that's quite common you have to do is to time things. So you have another family of interrupts which are generated internally within the processor called the timer interrupts. Let's run through what they are. All processors have a timing reference, which is the crystal, the basic crystal that runs the computer. Now that could be typically 10 megahertz, 20 megahertz from a microcontroller, 300 megahertz from Pentium. That's what these terms refer to. It's the actual basic crystal, quartz crystal oscillator that gives us our basic timing reference. Now that usually is far too fast for us to use in processing. So internally, there is always some fixed pre-scaler that divides it down to something that is more usable, and that is usually referred to as the system clock or the machine clock or the internal clock, but that is the timing reference that we're interested in. Different processors divide it down by different amounts. Now in terms of microcontrollers, I know that a PIC processor divides by 4, an Intel 8051 divides by 12, and a Motorola 8011 divides by 2. Whatever it is, you can just look it up in the book, but you know that the basic timing frequency available to you is always a division of the main crystal oscillator. Now that clock will then also, this is a fixed prescaler, I should say, that is determined by the processor itself, but then there is also another prescaler that is programmable. So under program control, you can load into this prestoler some other number of your choice. Different computers give you different capabilities. This is a generalization. A PIC processor will only allow you to load prestolers that are binary divisions. Other processors allow you to load any number you like. It does vary. Some of them actually don't even give you a prestoler. This is a general concept. Somewhere or other there will be a prestoler that gives you your basic timing reference. So out of this, we now have our clock set to our frequency, our timer, and we've managed to arrange that by setting up a prestoler. Somewhere or other in the processor there will always be a thing called a free running timer or the free running clock, and that is usually a 16-bit register. Now all this is, it just counts up. So we've got coming in our clock, a nice low frequency, it goes into a 16-bit register, and all that does is count. That means we can interrogate that clock anytime we like under program control and read the current time of day. It's very similar to the 8253s we've discussed earlier. You always get that. It's the key. If you don't have a free running timer or a free running clock, some way to get timing information, you cannot develop a real-time system on that computer. That's why most small industrial microcontrollers, well, all of them, include a standard, a mechanism such as this that gives us a free running timer that is derived from the basic system processor clock. And that is always accessible using a pointer from your program. This is always memory mapped, which means you can view it at any time using a pointer to that memory address. You can read that time, you can write it, you can reset it. Now why is this leading me up to interrupts? Because there are a whole variety of interrupts you can generate based on this free running clock. So if we have this timer, a free running clock, and I'm going to now refer everything to the free running clock. You take your crystal, there is a fixed prestoler, there's a programmable prestoler, and we've generated our own timing reference. So here is our timing reference at a frequency of our choice. And we have here the free running clock. Now, one of the most important interrupts you can get from this is the timer overflow. What that means is that when this finally reaches its terminal count, so it goes from FFFE to FFFF, and it wraps around. It's a 16-bit timer, and remember, computers are stupid. They don't know any number bigger than the size of the register. So if you add 1 to FFFF in hex, it wraps around back to 0 and starts from the beginning. What happens there is you have the ability to issue a timer overflow interrupt, if you so wish. That is something that you can easily do under program control. So what we can do, we've set up our basic system clock. We have a timer overflow. That means at regular intervals we are going to get a nice slow interrupt frequency. We can use that for many things. We can use that for timing our sampling rates from our ADCs. We can use it to schedule processes to happen. We'll look at that in operating systems later on. But the timer overflow is one of the most useful events that could occur, because it's a way of giving us a regular timed event, timing signal internally. This is the basis of our real-time executive, the fact that we can generate a nice slow frequency. So if we started at 20 megahertz, we can divide it all the way down through all these registers to give us something more sensible we can use. Typically, we would run a real-time executive at rates of, say, 100 Hertz to a kilohertz. That sort of range is what's important to us. And we do that with a timer overflow interrupt. Now, there's another type of interrupt that's quite useful. It's something that combines together an external interrupt with the timer. Because wouldn't it be nice, instead of having this interrupt occurring and we go off and process it, sometimes it's extremely useful to know exactly when that external event occurred. So let's assume we have here a rising edge signal from some external device. Let's say this is our switch or our brake or our pedal or our timer. Something has given us this rising edge event. Now we could process this using an external interrupt, and that could signal an interrupt service routine to start operating that services that external event. An alternative is to use a wonderful concept known as input capture. What input capture means is we still issue the interrupt in the normal way, but we take a snapshot, a copy of the free running timer at the event it occurred. You don't need to do this in your program, it happens automatically. So what happens is that on the rising edge event, that signals to the free running counter to take a copy, and it copies it into another register called the input capture. The input capture register. So what we have combined together is the rising edge external event, and we've taken a copy of the time. We've taken a snapshot of it and we've stored it in the input capture register, and that's done automatically. Your program doesn't have to do it, it's automatic. That means that when you finally get around to processing that external event, no matter how long it takes you to do it, you can always refer back to the log, the time it occurred, and so you can do some precise timing calculations, for example measuring an input frequency, by looking at the captured time in the input capture register. So that's a way of capturing the time of internal events. What about predicting the future? There's another wonderful use you can put these free running counters to, and that is the output capture concept. Now how does that work? Well, here we have our clock, our timing reference, and our free running counter just clicking over. And we have a register known as the output capture. Now the way that this works is that when the contents of the free running counter equals the output capture, we get an interrupt. It's a way of setting an alarm clock. It's a way of saying, right, we'll read what the time is now, we will add an interval to it, put it into the output capture and go away, go and do something else. That then times out. Why does it time it? Because let's assume the number in here was say 136 and we wanted to have an interrupt say 500 counts later, so we write into here using C star FRC plus 500. So there is our code, star output capture, a pointer to the output capture is set to, here's a pointer to the free running counter, the current contents of the free running counter, plus 500. Very simple bit of code. So we've set up some pointers and we say star output capture equals star free running counter plus 500. There's a single line of C code that loads the output capture register with the current contents of the free running counter, i.e. the time now plus an interval. And now we can go away. Having done that, we can go away, process something else. The free running counters counts up. When the contents of FRC equals the contents of the output capture register, that issues an interrupt. So what happens is we read the time, we load it into the output capture, we add an interval to it, and go away. When they count up, totally independent of our program, when they reach equality, it issues an interrupt, so our process stops what it's doing and it services the output capture interrupt. So it's a way of setting up an alarm to say, in so much time in the future, we will do this. And that's how you can schedule functions to run in the future. You can set intervals in the future. You can use it to generate output frequencies by precise timing. So if you need to generate an output frequency, you can use an output capture interrupt. So there's another family of interrupts for you. We've had external interrupts, which is a rising edge or a falling edge or a level. And we've got timer interrupts. The internal timer overflows. Or we have input capture, a combination of an input signal captures the time that something has occurred, and so our interrupt routine will then be able to read the actual time that that external event occurred. And I've told you about output capture events. With output capture, we set a time in the future. We read the current time, we add an interval to it, and sometime in the future, when the free running counter equals the output capture register, an interrupt is issued. So there's another time. Now these facilities, these tools, is probably more than enough to implement the vast majority of real-time requirements. We have the ability to react to external events, switches closing, switches opening. We have the ability to time precisely when things occur by using a free running counter. We can use the timer overflow concept to give us our sampling waveform, our real-time intervals, the time where we schedule tasks to occur in an operating system. We can time events in the future using output capture. But there are other types of interrupt. Let's have to think about what else you might get in the system. Well, more often than not, it's extremely useful for your real-time system to be able to communicate with an external PC computer logging system, something much slower. It's not important, it's just there perhaps for maintenance or supervision, and that's done with serial communications. The majority of reasonable microcontrollers, and that includes the PIC processor for which you have a data sheet, include as standard an asynchronous communications register through which you can implement RS-232 or some other form of asynchronous link. Some of the cleverer ones also do synchronous communications, so you can actually implement full-blown HDLC if you really are so inclined. But it's very rarely done. Normally people settle on just for RS-232 and a simple asynchronous link. Associated with the serial port, then there will be two interrupts. One of them is to tell us a character has arrived, and one of us is to tell us that the register is free to transmit a character. Now, why is that? Serial communications is very slow. Even if you're running at 19.2 bits per second data rate, that is still, in terms of real-time systems, slow. So what you want to do is you offload that problem onto a synchronous or asynchronous receiver port, and you let it do it on itself. So we have in our computer, here's our microcomputer. Somewhere or other, there will be a transmit buffer on which data is transmitted out, and somewhere also there is a receiver where data can come in. And this is typically 8-bit asynchronous data. That's how it's normally set up. Now, we can't afford to have our microcomputer continually monitoring the slow asynchronous link to say, has data arrived? The way it normally works is we have an interrupt, so that whenever a character is received, an interrupt is issued to say, "Oi, stop what you're doing, a character's arrived. Go and process the serial link," which could be a keyboard or a remote PC or a remote computer. But some slow data has now arrived. and it's all there, all 8 bits have arrived, and it says, oi, stop! I am the receiver interrupt, process me now, get the character. So we have associated with this that when 8 bits have occurred, we issue a receiver ready interrupt. Receiver ready interrupt. And that issues a call to the processor to say, oi, stop! There's something in the receiver, grab it now, read what it is, it might be important. So I'm important, look at me now. But that means that we're relieved of the task of handling the very slow, let's say 9600 bits per second, serial communications task. We don't need to grab each individual bit. It's happened automatically for us, and only when the whole character has arrived are we told it's going to happen by a receiver ready. That's a very nice task because it means we can get on with our job, and we know that if somebody wants to talk to us, either a supervisor or another computer, we know we're receiving an interrupt, a signal to say some data's arrived, service me. What if we want to send a message back? Well, if it's a very long string, we don't want to sit there while each individual character is clocked out. We can't afford to waste time handling something as trivial as the supervisor on an RS-232 port. We have more important things to do, controlling the car, controlling the machine. What we want to be able to be told is that the last character has gone, that the transmitter is free to accept another character. It's a form of flow control. And so associated with the transmitter will be a transmitter ready interrupt. And what that tells the processor is that the last character has gone, and now I am ready to receive another one. So what we can do is we can now implement a print spooler. This is how they're done. Very, very simple concept. The transmission part of the job is done independently to us with the asynchronous receiver transmitter block. We write a character into it. That's just a memory transfer. It's a single operation, a single line of code. Our next character to go is written into the memory block of the transmitter. So the transmitter is always memory mapped. And then we go away. Why? Because this 9600 bits per second is incredibly tediously slow. Our transmitter clocks out these bits very slowly, and when it's finished, it then gives us an interrupt to say, I've sent that character now, please give me another character. I want the next one. So the amount of processor time that is involved in spooling, in printing, in sending data out is extremely small. All the processor needs to do is to have a buffer where it stores the characters to be printed or displayed or transmitted, and a pointer. A pair of pointers move along. There's the end of it, saying that's where we are now, that's where we want to be. Here's the next characters to go. Every time we get an interrupt, we move the pointer along, output the character. So we end up effectively with a cyclical buffer. That's how these things are done. Here we have our print spooler memory. Think of these as little boxes. And we have a top pointer and a bottom pointer. Every time our processor wants to add a new character in, it puts it into the last character location and it moves the bottom pointer down again. Every time we receive a transmitter ready interrupt, our processor says, right, if the bottom is not equal to the top, that is, if there's some characters waiting to go, we grab the next character, write it to the transmitter buffer, and move the pointer down one. So whenever these two are equal, it means that there are no characters to go. And the only intervention of the processor is when we receive the transmitter buffer ready interrupt, we go off and say, are they the same? If so, nothing to be done. Switch off the interrupt, switch off the transmitter, there's no job for it to do. If they're not the same, we grab the next character, decrement the pointer, and then the transmitter will take over the job of transmitting our data. So that is a transmitter, a serial ready, transmitter serial ready buffer, and a transmitter receiver buffer ready flag. Very, very simple concept. So we've added to our list of potential interrupts. Now, so we've got external interrupts, timer interrupts, serial buffer interrupts. What else might we have? Well, one that's quite important is a watchdog interrupt. A watchdog. Now, in the section on system integrity, we will discuss the role of watchdogs. Usually, they're an external device that monitors the processor and forces a reset, a bootstrap reset, if it sees fault. Some processors, though, actually have them internal within the actual processor itself, and that means that instead of hitting the reset line, in fact, they can issue an interrupt, and you can have a watchdog interrupt that resets the processor and forces it to go to an interrupt service routine. What else could you have? Well, what about these wonderful I/O devices we need? Analog to digital converters, that's a common one. There's a whole family of processors on the market now that include inside the processor analog to digital converters, analog inputs. Now, as we've seen, SARs, dual slopes, they're quite slow things. You don't get flash ADCs in processors, they're too expensive, but you do get dual slope and SAR type ADCs, usually SAR. There is a finite conversion time for these things, typically at kilohertz to 10 kilohertz, so we cannot afford to wait for them to happen. So what happens is they issue an interrupt request. Let's see how that works. First of all, we'll look at the traditional design. The traditional design is that we would have a microcomputer. There's the ADC. Somehow or other, it lives on the data bus. There is a signal that goes to it that is the start of conversion, and there's a signal that comes back that is the end of conversion. So this is the mechanism by which we control the actual process. So if you look at it in terms of timing, start of conversion is normally low, end of conversion would also be low. If we take start of conversion high, that starts the conversion process off, and when it's finished, the end of convert signal goes high to signal that we have completed the conversion. These are effectively the handshake signals. You could do this with straightforward digital I/O if you wanted to. All ADCs are slow. They're always slower than the processor. So using the start of convert and the end of convert signals, you can do it simply by digital I/O. Pulse the start of conversion high, the ADC does its job. When it's finished, it signals back, I finished, end conversion, and then you can read the data. That is the standard way of doing it with a bus. You could move on from that, couldn't you? Why sit there polling the signals? This is the only way you can do it. That's what I've described as a polling mechanism, whereby we have start of conversion goes out, end of conversion comes back. What's the program do? So practically the program is saying SOC equals 1, SOC equals 0. That's issued the pulse. While not EOC sit there doing nothing. So what we're doing is we're waiting for the end of conversion to go high. And when it finally goes high, now we can get ADC data. Now that mechanism is known as polling. Why is it called polling? Because we're forever polling, asking a question, requesting information from the end of convert signal in a tight loop. So what's going to happen is our processor, from all this time there to that time there, it's just wasted. It's just sitting there in this little loop, waiting for the end of conversion to occur. What a waste of time. What a terrible waste of processing time. You've got a cure for that now. you could use the end of convert signal and take it to an external interrupt. So what should we do? We'll have start of convert comes out, and the end of convert, instead of going to an input pin, we take it to the external interrupt instead, and we say that will be rising edge sensitive. So now we can output our SOC and go away. We can do something else. And we can rely on the external interrupt that will be generated when the EOC occurs to signal us to go to our get ADC data. The difference is that that get function, instead of being part of our process, is now an ISR, an interrupt service routine. It's a parallel process. It's totally independent of our main body of our program. Now, I'm going to put these to one side. I'll return to them later because there's some important analysis we've got to discuss about this structure in terms of data handling. Why have I raised this now? Because many processors now, rather than having a separate ADC and the processor, they incorporate the ADC in the processor itself. So what do you actually get? This has been one of the great breakthroughs of the last few years, actually, is a microcontroller whereby one of the input pins, instead of being a digital input, in fact is capable of taking in an analog signal. And that signal goes into an internal ADC. It's actually in the chip. It's been integrated in the chip. And when the end of conversion occurs, that issues automatically an ADC interrupt, and then we can service that interrupt and then return from the interrupt internally. So it's all done for us. It's all wrapped up. Computer technology has gone in two directions. We have these incredibly powerful processors such as Motorola 68000, the Pentium processor, and similar devices where they've gone for speed, more and more speed, bigger registers, cleverer calculations, multiple processing, including mass floating point coprocessors onto the device. Thus you have the PCs, mainframe computers. The other direction it's gone in is that this ability to miniaturize and to put lots of things in microcontrollers. We've kept the processors simple, but integrated into them all of the external architecture we need for a real-time system. Parallel I/O, timers, ADCs, pulse width modulation, and all these other techniques you will find embedded into the processor itself. Today's modern microcontrollers are almost standalone parallel processors in their own right. They can't do clever maths, but they can control the external events around them using these hosted facilities. And the example here is the ADC. You now have that integrated into the computer itself, so that the ADC interrupt tells us the ADC routine, the ADC has completed its job, and it's all memory mapped. So we can go straight to the registers. The ADC, not only does it do the conversion, it drops the results into little boxes for us in the memory of the processor. We can just read it using a pointer directly to the memory location, and we don't have any of the problems we have with the old external devices, having to transfer data back and forth over a parallel bus or over an I2C link. What else is there? Well, we've covered sort of the bulk of what we've got to be worried about. One other thing we should take account of, and you should be aware of, power failure interrupts, power save. Computers crash. Nothing we can do about that. We wouldn't accept it in a used car. I mean, why it is when we buy a used car, we find something wrong with it, we go and complain to the manufacturer. Yet when our computers crash, we just say, ah, it's a computer. We just accept it. I don't know why. It's a crazy concept, but the computer industry has managed to accept us, to manipulate us so we're prepared to accept dodgy goods. They do crash, they do die. One of the main causes of failure in real-time system It's in fact something very simple. The power supply fails, a power supply interruption. If the power from 5 volt dips a little bit, the computer stops running. A very important group of interrupts are those that monitor the power for us, and if they detect it drooping, they issue an interrupt. Now, why is that? Well, if the power supply starts dropping, you've actually got probably a couple hundred milliseconds of sufficient power left to do something. So if we detect, say the power's at 5 volts, if we detect it's dropped to 4.5, the processor, believe it or not, will still keep running down to about 3 volts. While it's dropping, we can make things safe. So the role of a power fail interrupt, again it's internal, as soon as it sees the power is drooping, it says, stop! The power's going away! Help! Do something. It stops what you're doing immediately. You go to an interrupt routine, a power fail interrupt routine, whose role is to save any data that's crucial to you, switch off any machinery, and going into a safe situation. And remember, in real-time systems, you're the programmer. It's your responsibility to make sure things are safe. And you must take into account the effect of a power failure on the system, and you normally have to create a standard of power fail interrupt that gracefully decays, gracefully shuts down your system, switches off any motors, valves, actuators, turns off the gas supply, whatever it is. You've got 100 milliseconds or so to do it. That's plenty of time. You can get lots and lots of instructions done in that time to make things safe. Perhaps you even save a log to say, at such a time I had to shut down due to power failure. Here's the data, the failure information that will be processed later. That's the role of a power fail interrupt. So there's a whole host of them. So let's just review this, and then we'll look at how they're handled. Interrupts, they're external events. They're out of our control. They just happen. No matter how much you might want to write a nice structure for your program, you cannot stop the outside world intervening. It's asynchronous. You can't stop it. They're there when they want to do something, and they will do it. They will signal, it's time for me to go. And you've got to process them. So our structures have to operate asynchronously with parallel processors. And what actually happens, a real-time system, the software structure, isn't usually some nice threaded code. It's usually a whole host of totally independent interrupt functions that occur whenever they want to happen, and somehow or other we have to create the data structures that allow these asynchronous events to communicate with each other, to pass data backwards and forwards. It's true parallel processing. That's what we need to cope with. So let's list what we've got. We'll just run through a summary of the interrupts we've discussed. We've talked about external interrupts: rising edge, falling edge, level, sensitivity. Timer interrupts, that's timer overflow, that's where the counter has reached the end of its terminal count. We've talked about input capture, so we capture the actual time at the event the external event occurred. We've talked about output capture. There are other parameters we could discuss here, such as the ability to auto-reload a count, the fact all these counters are memory mapped, but that's been discussed elsewhere. These are the tools available to us. ADC is another example of an interrupt. So we actually have an interrupt that occurs on the enter conversion, and that tells us to go and get the data. Serial interrupts. TX ready, receiver ready. That tells us a character has arrived. This tells us the transmitter buffer is free and we can now transmit something. Power fail. As the power supply starts drooping, we get an interrupt, and that tells us we have, say, 10 to 100 milliseconds left to do something, so we can switch things off, make them safe, sort them out. There's a whole host of them. Pulse width modulation, watchdogs. You can get PWM interrupts. Remember, PWM is this concept whereby we have a variable marked space in a fixed frequency. So it's sometimes useful at the end of each of these periods to have an interrupt in case we want to reload a new PWM period. Watchdog. So we have a little internal timer, and unless we reset it inside our software, it will eventually time out, and that will issue a reset to restart the processor off. There are others. You can pick up a book and you'll find there are lots and lots and lots of interrupts. How does our program know what is the cause of the interrupt? How does it know what to do? How does it handle these interrupt service routines? For every single interrupt in the processor, that's available. Some processors only have one or two, some can have as many as 30 or 40 different interrupt sources, or more even. For every single interrupt, there is a unique part of the processor's memory map where the interrupt service routine begins. And that's a permanent constant, it's fixed. And this is all held in a thing called the vector table. Somewhere in memory, this is code space, it's not in RAM, it's not in data, it's in the code, there is a thing called the interrupt vector table. And for every possible interrupt, there is an entry in this table, and it's fixed. So for example, what happens when the system first powers up? Believe it or not, conceptually, the main switch on of a computer is also an interrupt. Conceptually, it's the same. It's the first interrupt, because we were doing nothing, and then we were woken up. That is the power on reset. So the main body of the program is itself only a grand example of an interrupt, from being asleep, off to on. And there is always a specific point in the memory map that the processor goes to start running the program. If this was an Intel processor, it would be down the bottom at a location 0. And that is the power on reset. It's always there. It's always in the same place. Every Intel processor, from the humblest microcontroller, the 8048, all the way through to the Pentium, the power on reset vector is always the first 2 bytes in the memory map. It's always down the bottom of that location 0, without fail. For every processor, there is a fixed position in the vector table for that location. So somewhere else, in a fixed location, there will be the receiver ready vector, or there will be the external interrupt vector. And this normally lives in the bottom 256 bytes of code, from 0 to 256 are all the vectors. These are at fixed positions. So you know that whenever a specific interrupt occurs, it will go to a known position in the vector table to find out what to do next. And what do we do next? Well, the contents of this vector table always is an address. That is for you to write in, because what this tells us is that is where we will find in the program memory the ISR, the interrupt service routine, that relates to that event. So a fixed position, let's assume here this is the timer overflow interrupt. The timer overflow interrupt will always look in the same box in memory for the pointer to where the interrupt service routine is. So the interrupt vector table, that is fixed in memory. It's an absolute memory location. You know, you can go to the manual of the books, the processor, you can look it up. It says, right, serial interrupt, vector interrupt will always be at memory location such and such. It's a constant, it's a universal constant. It's in the data book. But you write into that memory location the actual true position of where the program is, where the interrupt service routine is. It's a redirection table, really. That's why it's called a vector, because it points us to where we have to go. So what happens is, an interrupt occurs. This is a signboard. It's in a fixed memory location. We go to the specific point in that table that tells us what to do next. There we will find an address which our program, that's your job, you have to put that address in there, that points us to the code space, and there that will then hold the interrupt service routine. And most modern compilers for microcontrollers actually automate this process for you. As long as you create a label that marks the start of the interrupt service routine, you state that that label exists in the memory block and it does it for you, it will generate the code for you. So a lot of this happens automatically. But that is the role of the vector table. It tells us where to go. Now what happens? There we were, happily running our background process, doing what we want to do. And along comes an interrupt. So here we have nice program code, line by line, working our way down it. And all of a sudden, an external event occurs, an interrupt, and it says, "Oi, stop what you're doing. What are we going to do? What have we got to do?" Well, we have to, if this is our interrupt service routine, we have to somehow get to this interrupt service routine, execute that code, and get back to where we were in a totally non-destructive manner. Our background process must never know this occurred. How is it going to do that? Well, it makes use of a feature that all modern computers have, a stack. A stack is an area of data memory where we can temporarily store variables and get them off later. So what do? Let's draw the stack. And we have a thing called a stack pointer that points us to the stack. When the interrupt occurs, the first thing it does, we'll list all these processes, it automatically disables all other interrupts. We don't want other interrupts to interrupt our interrupt, or we're going to get in a real pickle. So we have to automatically stop all other interrupts occurring. We've got to get our current interrupt out of the way before we allow others to happen. So this happens automatically. Interrupts are disabled. Now what happens is, we were here, we need to save the program counter on the stack. Why? So that when we finished our ISR, we need to know where to go back to. That happens automatically as well. So interrupts are disabled, and the current contents of the program counter is stored on the stack. And now the stack pointer will point to the next free location. That's all automatic. What's the third thing we've got to do? We need to get the vector. So our processor goes to the vector table. It knows which entry to go to automatically, because every possible source of interrupt has its own unique entry in the vector table. But somewhere in here, there will be an address that we have written in, and that points us to our interrupt service routine. So now we've disabled all interrupts, we've remembered where we were, we go to the vector table to find out what to do next, and that is an address that points us to the start of the interrupt service routine. Now what do we do? Well, the first thing you've got to do is you can't run your ISR. Why? Because your ISR is going to mangle up the processor. It's going to start using resources. It's going to destroy the contents of the accumulator. It's going to overwrite status flags, just as carry or zero. It will use registers. It will change things. And we can't let that happen. Because when we return to our process, our background process, it must never know anything's happened. It's got to be totally independent of it. Everything has to be clean. So before our ISR, before our interrupt service routine starts mangling away at the processor, it's got to take a copy of everything it's going to use. It must say, neatly store away everything it finds in another little box. And then it can mangle at its own leisure, as long as it then restores all the status before it returns to the main body of our process. Now, most of what I've told you up to now happens automatically. Only you, the programmer, knows which bits of the processor, which bits of memory, which registers your ISR is going to use. So only you know what bits of memory or registers you need to copy. So you've got to do it. So before we can do anything, we have to save the status. That is, the ISR has to do it here as a bit of preliminary code. It has to save on the stack anything that it's going to use. That could be registers, it could be memory. I don't know what it is. It's up to you. It's your program. Only you know which bits of the processor you're going to use. So before you use it, you have to take a copy. You push all the contents of the registers, the flags, the memory you're going to use onto the stack. And now that you've taken a copy of everything, because you're very good and clean, you tidy up after you go. Only now can you actually execute the body of your interrupt service routine. When you've finished what you're doing, you should tidy up. You've taken copies of all the registers and the memory that you mangled in your process. So now you should be very good and you should restore them all. So you clean up, you tidy up, you restore the status. Once you've restored the status, you can now return from the interrupt. It's not a normal return, it's not the end of a subroutine. It's usually a special instruction, return from interrupt. That means you go to the stack, you find the program counter, you return to where you were, and you finally automatically, so now we return RETI and we re-enable our interrupts. That is the complete process of an interrupt service routine. So there's a penalty. You've got these wonderful parallel processes, but there's a lot you need to do. Let's run through that whole lot again. An interrupt occurs. In order, the events are 1. Disable all interrupts. 2. The current program counter is stored on the stack. So there we were running through our routine, and then the interrupt occurred. So that program counter must go into the stack. 3, we go to the vector table. The vector table is this other body of code, fixed, but it tells us where to go to. 4, we've now made our way to our interrupt service routine. What have we got to do first? Before anything else, we must save status. We must save the contents of all the registers, the memory, anything we're going to use must go into the stack. Now we can execute our interrupt service routine. So we do what we want to do, but before we exit, we have to restore the status. Everything we stored in the stack we now take out. We tidy up, we clean up, we put everything back where we were. And finally we do a return from interrupt That means we look at that program counter, we return back to where we were, and we continue with our process. When we exit, we automatically re-enable the interrupts. That happens automatically. You must, as an essential task, you must understand how to write interrupt service routines, because the bulk of real-time systems consists of lots and lots of interrupt service routines. So, before I move on to data handling, let's have a summary. Most programs, good design practice tells us we want a structure. We have a nice program, series of branches, series of questions. We always know where we're going. And you should retain that concept as your main background process. Anything that is unimportant, you should write as a structured program, know where you're coming from, know where you're going to. However, real-time systems consist of parallel processes, lots and lots of interrupt-driven functions from different facilities, peripherals around the processor that are responding to events in the outside world. External interrupts, ADCs, power fails, watchdogs, pulse width modulation, whatever they are, timer events, they're all impinging, they're asynchronous. So we actually end up conceptually with a main process that is surrounded by these tiny little timer interrupts, ADC interrupts, external interrupts, but they are separate entities. They're all parallel processes. The interrupts will pop up when they want to occur, seize control of the processor, kick everybody else off, do what they want to do, and then run away. And it's up to you to write good structured program code that ensures that that happens cleanly. That when that event occurs, it happens, you get it out of the way as quickly as possible, and then you return to the main body of the program. When I say quickly as possible, you may have noticed if you go to the data sheet for the PIC processor, I'll just zoom in on any page, any instruction, any one, it doesn't really matter. You will find it always you get a line that says cycle time. This tells us how long it takes, how many machine cycles it takes for that instruction, whatever it is, to occur. Why is that? Because part of the job of designing an interrupt service routine is to calculate how long it takes to execute. These things are parasites, to be frank. You've got a nice structured program and a long conscious interrupt routine that snitches control of the processor. You want them out of the way as quickly as possible. That's why a microcontroller book will always tell you how long the instructions take. It allows you to calculate in advance the processing time needed for the interrupt service routine. And quite often you sit down there and you have to work these out yourself, and you count the machine cycles in order to get it as fast and as quick as possible. And when it does it, it's got to be clean. So you have to save the program counter, save the status, do what you want to do, and restore the status, and then you can move on. How do we know where they are? How do we distinguish in between them? With the vector tables. The vector tables tell us where they are, where to find them, what to do. So those basic concepts of types of interrupt we'll come across, and how a basic interrupt service routine should be structured. And let's continue with our discussions on interrupts and how we handle them. Now, how does the processor know which interrupts are available and which should not be used? That's one problem we have to discuss, because there's a whole host of interrupts available, and you may not necessarily have all of them active at any one time. The other thing we must discuss in great detail is data handling. Now let's deal with that one and get that one out of the way first. Let's go back to our ADC. If we were using a polling technique, how could we handle this? Remember this is not an interrupt one. This is where we have a starter conversion line goes out, tells the ADC to start, and then we just waste time waiting. When the end of conversion occurs, we can get that ADC data and process it. How do we handle that data handling? Well, that's no great problem, is it? It's a single function, it's not parallel processing, so we could easily declare in our data area ADC data. ADC data normally is 16 bits or 12 bits, so it's going to come as a high byte and a low byte. Bear in mind, I'm talking about microcontrollers. They're normally byte-orientated machines. They don't have words or integers. If you need integers, you have to achieve it by concatenating together bytes. So we would normally have an ADC high, which you would declare as, say, a character variable, and there's a character variable for the low. And in order to create an integer variable, we would have to combine the two together. Now this is dead easy in terms of if you're going to poll. All we do is just say start of conversion equals 1, start of conversion equals 0, so that's easy enough, while not end of conversion, so we just sit there wasting time, and then finally we can say, right, ADC data high equals whatever the address is. Remember, the ADC is sitting externally on the data bus. Its registers will be memory mapped, so there will be some address there, let's say ADC high address, so that will read that memory in, and then we say ADC data low equals ADC low, so we get the lower part of the data into our memory, and now we can process the data. We could offset it, scale it. There's no problems with the memory map here. Because it is a single process, everything exists as the same entity. So we can declare our data variables, we copy the data over from the ADC memory map into our local memory map and process it. We can just run. That's what you achieve with polling, very simple data structures. You can't do that with interrupts. Why? Because you never know when the blasted things are going to happen. Now let's look at this particular routine again. Let's assume instead of having a while end of conversion, we're going to use an interrupt. So we'll have an ADC interrupt. So what we're going to do is we're going to connect the end of conversion to an interrupt routine. What would happen if we were happily running through this in our background routine and the interrupt occurred here? It could do. You don't know when the interrupt is going to occur. This is the basic definition of an interrupt. They can happen whenever they want. So you could be happily reading the data from the ADC in your background process when all of a sudden the next conversion finishes when you've only got half the result and it updates the numbers. And because you are a good programmer, you've written an interrupt service routine that is totally transparent, you don't even know it's happened. So what will happen here in our current example is that we would get this ADC high value would come from the conversion at time n-1. The interrupts occurred, it's updated the registers here, and now we get the data from time n. Very easy to happen, because what you have to remember is they're parallel independent functions. Each of them must have their own separate data area that belongs to them. You cannot share data memory locations between parallel processes. You have to create separate entities, separate data areas for each independent routine. So the structure I've just drawn here for polling, that would work, but for interrupts it won't, because you never know when an interrupt will occur. What you must do is you have to have separate memory locations. So here we have, if this is our background process, and it's got to process ADC data, and then move on, and if here is our ADC interrupt, our interrupt service routine, on the end of conversion, there's the end of conversion, this routine comes into life. It will grab the data from the ADC, and then it will exit. This routine is not allowed to access that data. It's illegal for it to do it. Why is it illegal? Because the ADC interrupt could happen anytime it wants. And we don't know when it will happen, and it will update the ADC active data areas. We can't come along and just take copies of it whenever we want, because that interrupt could have paused us while we were getting it, in the middle of it, and updated that data. So what we will get is rubbish. We'll get a bit of the old data, a bit of the new data. And this is true for any interrupt. All interrupts must have their own secure data area. It's a separate function, it's a separate process. You mustn't share data areas between parallel processes in any structure, in any program. So if our background process is not allowed to access the ADC data, how can we achieve the data transfer? How do we get this data into the background routine in a safe, secure manner? Well, there are many techniques that have been proposed, and I'll only describe one of them. The basic concept is always the same. What you have to do is to keep the interrupt data area independent of the background process. And in between the two, you pass a message, a semaphore, and the message contains the data. So parallel processes have to have structures that allow data to pass between them, and we do that using a post box and a semaphore. So let's draw our processes again. Here we have our interrupt service routine. And here we have our interrupt service routine data. That is the basic concept of an interrupt service routine. And then parallel to that, we will have our background process. Somewhere or other, it requires to get the ISR data because it needs to process the ISR data. Now, I've made this quite general now. It can be any ISR. How do we get the data from there to there? These are parallel processes. They can happen at any time. They're not synchronized. We don't know. What you have to do is to set up what is known as a postbox, a safe area of memory through which they communicate. So the ISR it keeps its own data separately. This is a shared bit of memory, and it puts a copy of the ISR data into that memory location. And like a traditional mailbox, there should be a little flag on it, and when it's full, it should set itself true to signal to the background routine, hey, new data is available. And what the background process has to do is now it can safely take a copy of that, set the flag back to false, thereby freeing up the data box. So what we have using the data box, the post box technique, and a semaphore is a mechanism to transfer data between these asynchronous processes, just like the mail. So our asynchronous interrupt, it leaves some data in a known area of memory. When it passes through, it leaves its result, and it sets a signal true, say, hey, the post box is full, please come and get the data. When the background process finally gets around to wanting that information, it looks at the flag. It says, right, is the semaphore true? If it is, great, there's new data for me. It takes the data copy out and copies it into its own memory location, and then it clears the flag, so it frees up the post box. It's like having a left luggage office where both processes have a key. The interrupt routine fills the left luggage box with the data and locks it up, sets the flag true. Only the background process can unlock it. So it says as soon as it's true, it retrieves the data and frees it up. And we can use the flag as our flow control for our signal. So let's assume the background process hasn't emptied the box. When the ISR comes round again, it can see the flag is still set, so it knows the last block of data hasn't been read, hasn't been used. That may be of importance to us. So we can use the postbox technique. Let's go back to the picture. Our interrupt service routine has its own data area. The background process routine also has its own data area for that same variable. These are identical variables but independent memory locations. And data is passed via a postbox. When the data is available, the ISR puts it into the postbox and sets the signal true. That tells the background process data is available. When it gets around to handling it, it can empty the postbox and set it false. And you can use the same process to signal back. If the background process needs to leave messages for the ISR, it can put it into an outgoing postbox and it can set the flag true to say, hey, I've got some data for you. The next time the ISR occurs, it looks at the flag, it says, oh, there's some data for me. And so it grabs those instructions, sets the flag to be off, false, and that signals back to the background process that the data's been read, the message has been passed. It's a very simple process. And what we have, two separate parallel processes with their own data area communicating to each other using postboxes and semaphores. You must do it. You must never ever allow parallel processes to share the same data area. Otherwise they can't get on with their own job. So you have to have a mechanism to move data backwards and forwards. So now let's go back to our comparison. Our ADC, if we had polled it, the great advantage of polling is we have a very simple data structure. You can share the same data areas because you're not both playing with it asynchronously. So the ADC routine can put the data into a memory location that you can then go on and process. Simple data structures, but you waste time while you wait for events to happen. If you want to save time, you want efficient timing, which is usually more important, you break those into two. A background process and an interrupt. Much faster, far more efficient, but horrendous data handling. Because you have these parallel processes that can occur at any time they like, they mustn't share data areas. So you need to set up postbox structures, semaphores and data areas to pass parameters backwards and forwards between the parallel processes. So, interrupt routines, very fast, very efficient, but complex data structures. Polling, much slower, very inefficient in processing time, but very simple data structures. That is the main lesson of that section. Now let's consider the other question. What was the other question? How do we know which interrupts are active and inactive? This is going to lead us into some more interesting ways of processing interrupts. All processors that have multiple interrupt sources in a vector table always have a register which is used to signal whether or not an interrupt has occurred. It's the interrupt status register. The interrupt status register is a block of memory typically 8 bits, might be 16 bits for more complex processors, and this is at a fixed memory location, so you can access it with a pointer, and for every possible interrupt there is a single bit related to it, so the external interrupt will have a bit somewhere. The timer overflow will have a bit somewhere. And whenever any of these events occur, whatever it is, be it the timer overflowing, the ADC, the way it works is that that individual bit in the interrupt status register goes from a 0 to a 1. So the ISR, the interrupt status register, stores the current state of all interrupts that are pending, waiting to be executed. Now that is always there. So even if an interrupt is disabled, you've no interest in it, there is a memory location anyway that tells you whether it's happened. So let's assume you've switched the ADC off and you're not interested in it anymore. If it's still running, it carries on setting this bit every now and again. So we have a status register. Now, how can we use this status register? It is used in combination with another register called the interrupt mask. The interrupt mask. Now, as I said, for every location in the status register, there is a bit assigned to a specific interrupt. So if this is the bit for, let us say, the external interrupt, when that rising edge is true, that goes to a 1. And that is signaling this is occurring, this event has happened. The mask register, again, you can access it through a pointer. That is used to enable or disable specific interrupts. So if you were to write 00000 into it, then that interrupt will never be seen, because only if both the status is true and the mask is true will the interrupt service routine be executed. So the status register is used to store all the interrupts that are currently pending, and for every interrupt there will be a unique bit in the status register. Combined with that is the interrupt mask register. Only if the mask is true will the interrupt service routine that is required by that event occur. So you have to have both the event occur and the mask has to be set true to issue the interrupt service routine. So what does the mask give us? The mask gives us the ability under program control to enable or disable any or all of the interrupts at our choice. Now when any processor charges up, switches on, the whole of the mask is always set to 0 because all interrupts are always disabled automatically on power up. It's your job as the programmer to enable the relevant interrupts that you require for your particular real-time routine. Whatever it is, you've got to do it. So you have to go to the interrupt mask if you want the external interrupt, the timer interrupt, the serial interrupt. You have to set up the mask to allow them to happen. And when they occur, only if both the status is true and the mask is true will the ISR be called when you implement the actual interrupt service routine. So that's how you can control which ones you want. Now there's some other features here. This means that you also have the ability, if you wish, instead of allowing ISRs to occur, you can poll them, which means that you, instead of using the mask to call interrupt service routines, you could just look at the contents of the status register. You could poll the status register. So you actually have the ability, if you want to use these wonderful features in the processor, timers, counters, PWM, ADCs, but you don't want to get involved in the horrendous data handling problem of interrupts, multiple functions, parallel processing with semaphores and boxes, you don't need to. Because all you need to do is to poll status, the contents of the interrupt status register. That is dynamically telling us whenever an interrupt is pending. And all you have to do, instead of allowing the interrupt to occur in an unstructured, asynchronous manner, you can execute them in turn within your own background program whenever you want. So you've got actually the best of both worlds. The status register tells us if an interrupt has occurred. You can either use the interrupt mask to allow them to issue the interrupt service routine, or you can simply poll the contents of the status register in your program and execute those programs whenever you want in a more structured manner with a much simpler memory data handling structure. So there are the two options for the interrupt handling. Either you can let the ISRs occur, or you can poll them through the interrupt status register. Now let's add in one more degree of complexity, because some interrupts are more important than others. Timing interrupts are usually very important, but something else that's very important, hitting the brake of my car is important. So there's the third register you ought to know about. We have a status register that tells us whether an interrupt has occurred or not. Associated with the status is the mask register, and this is used to enable or disable specific interrupts. And finally, there is a priority register. It's usually only one bit. You normally only get either a high priority or a low priority. And what that means is that if there's multiple interrupts have occurred, say that one and that one, the one that is executed first is the one where there is a 1 in the priority register, because that means that that is a high priority task, whereas a 1, 1 and a 0, that would be low. So if two interrupts occur simultaneously, the arbitration between them is determined by the contents of the interrupt priority register. Very rare actually you would get into a system that's so complex that you would use priorities, but it is there as a facility if you wish. So what have we learned with this? We have a status register that tells us whether any interrupt is currently pending, whether it wants to be executed. We have a mask register which we can use to individually switch on or off individual interrupts. So we have a choice. We can either let the interrupt occur, or we can poll the status register. Finally, if multiple interrupts occur, how do we arbitrate between them? Well, the easiest way is you have a priority register that tells us which interrupts are the high priority and which are the low priority. So that ends the discussion on interrupts. What have we got to is that we have now the ability to have a parallel process, a whole series of parallel processes, and we end up with conceptually a main process surrounded by interrupt service routines that are servicing the peripheral devices of our system. ADCs, timers, external events, power fail, and these are all communicating with each other, not directly, but via data structures that involve the use of post boxes and simple semaphores. So we have parallel processes happening at any time, we don't know when they're going to happen, and post boxes that pass the data backwards and forwards between them. Now, before we finally complete this, we must give some consideration to timings. How much time is there available for an interrupt to occur? Well, let's assume here's a real-time system, and I'm going to assume that this is an interrupt, that's an ADC interrupt, and let's assume that we have to sample the data once every 10 milliseconds. So here we have an interrupt at 10 milliseconds, 20 milliseconds, 30 milliseconds, 40 milliseconds. That's going to happen every time. You must sample the data at regular intervals. So let's put in our little ADC routine. Actually, I'll put that one. So that's 40, there's 50 milliseconds. Now, how long is the ADC routine? Well, I'll just take a guess. I don't know how long it is, but let's assume it's 5 milliseconds long. That means half of the time slot is given to the ADC. So let's assume there's our 10 millisecond gap and 5 milliseconds is taken up by the ADC. Let's also now assume we have some other interrupt, let's say some external interrupt, and it occurs once every 50 milliseconds. So once in this block, this will occur. So we have an ADC routine happening once every 10 milliseconds, and it takes 5 milliseconds to occur. On top of that, we have some external interrupt here. It's going to happen once every 50 milliseconds. And my question to you is, what is the maximum amount of time allowed for that external interrupt to execute in? Let me draw the picture again, because it was getting a bit messy. And we'll have something a little bit more readable. Here is our ADC interrupt, occurring at 10, 20, 30, 40, 50 milliseconds. And whenever it happens, it eats up half of the available time. So there is the ADC routine. It's taking 5 milliseconds to do its job. And I've said that on top of that, we have to have another interrupt that occurs every 50 milliseconds. How much time is available? Well, the simplest answer that people often go for is to say, okay, we've got 50 milliseconds total, we've got 5 ADC routines that occurred, so in those 50 milliseconds, 1, 2, 3, 4, 5 ADC routines, 25 milliseconds has been taken up with the ADC. So that means there's 25 milliseconds left. So surely our other interrupt, you would think, has got 25 milliseconds to do its job. And therein lays the greatest fault in interrupt design, because that will not work. Why will it not work? Well, let's assume we've said, all right, every 50 milliseconds, there's 25 milliseconds spare. That's how long our other interrupt routine could be. Let's assume our other interrupt routine then took 10 milliseconds. Well within the time we've calculated. Now go back to the timing diagram. What happens here if we do our ADC routine and now we tack on a 10 millisecond external interrupt? What's happened to that ADC routine? It had to happen there. It was a sampling system. It's now going to be displaced in time to some time later. It's pushed forward. It's pushed out the way. So you cannot simply allocate all the remaining time to the slower interrupt, because if you did, the fast interrupt could be displaced. I mean, it could be even worse. What would happen if you had once a second, there was a 100 millisecond data dump to a tape streamer? For the whole of that 100 milliseconds, all other interrupts are blocked out. You cannot allow that to happen. Now, in fact, there is a very simple rule. If this is the rate of arrival of the fastest interrupt, then all interrupts, regardless of their execution time, must be completed as fast as the fastest. It's got to be. If all your other interrupts were to spread it out and take longer than the rate of arrival of the fastest interrupt, you would displace the fast interrupt from its required time slot. So the rule is the sum of all of the execution times of all of the interrupts in the system must be faster than the rate of arrival of the fastest interrupt. What this means is that you have to look at what is the fastest interrupt. If this is the rate of arrival of our fastest interrupt, then all of our interrupt routines, regardless of how long they take, must be executable within that time frame. Because if that wasn't the case, you would displace the next time of arrival of the fastest interrupt. Why have you got to assume this? Why? Because these are asynchronous. It is possible, and it will happen, that at some time in the lifetime of your program, every interrupt statistically will become active all at the same time. It will happen. You may not want it to happen, you may hope it doesn't happen, but it will. Sooner or later, the time will come when they all coincide. And if they all coincide, they've all got to be executed and got out of the way before the next fastest one arrives. So therefore we get this rule, that I've drawn diagrammatically there, the sum of the execution time of all your interrupts must be faster than the rate of arrival of the slowest interrupt. It's essential. It's absolutely essential, or it will not happen. So let's do some sums on this, and we'll look at a real situation. So let's now consider a real problem, a real timing example. It's not uncommon, but this is just indicative. Sort of data you might have. Let's go back to something that's very important, an ADC routine. An ADC routine is a regular sample event. It must happen within certain time periods. So it's probably the fastest. It's the data acquisition. Let's assume it takes 100 milliseconds. It occurs every 100 milliseconds, and it takes 50 milliseconds to execute. So this is the rate of arrival, and that is how long it takes. Let's assume we also have another interrupt, not very important, a print spooler, something like that. It occurs every 500 milliseconds. And so my question to you is, how long, what is the maximum amount of time that this must take? Well, the rule is that the total amount of time available for our interrupts mustn't exceed the rate of arrival of the fastest. Therefore, the maximum amount of time you can allow for a printer interrupt is also 50 milliseconds, because that plus that must not exceed the rate of arrival of the fastest interrupt. Now we can add another little figure in there. So this means that per second, sometimes it's easy to look at in frequency, this will happen 10 times a second, and that will happen twice a second. So in one time slot, let's say 1 second, the total time here taken by the ADC over a 1 second period is 500 milliseconds. 10 occurrences of the ADC per second, each of them 50 milliseconds long. 500 milliseconds processing time is devoted to the ADC. What about the printer? Well, it happens every 500 milliseconds, that's twice a second. Its interrupt service routine is 50 milliseconds long, so that means that 100 milliseconds of processing time has been devoted just to the print spooler. Let's assume we have a background process, and it takes 300 milliseconds to execute its functions in every second. Because all background processes, you still need to calculate the time. So in a 1 second period, 300 milliseconds has been allocated. So the question is, how much time is available to extend the background routine? Well, you have to sum all of these. You have to assume all the ADs, all the interrupts occur, plus you add in the total amount of time for the background, and that tells you how much time is left. So 5, 6, 7, 8, 900 milliseconds per second. So the total amount of processing time left available for you to do something else in the background is 100 milliseconds. Now, because the background routine can be interrupted by the processor, it is allowed to spread out its functionality. It doesn't have the constraint that the interrupt routines have of they must be completed at that fast rate of arrival. So the background routine can make use of all the little gaps there are between the interrupt routines. So ideally, you want to get as much as you can into the background routine. I'll run through those timings again. I'll show you that problem again. It's a typical problem, and I will also add it's a typical exam question. As you'll see if you read the exams, there are copies of the exams at the back of the book. You can look at some old exams if you so wish. So let's give that information again. We're given that we have an ADC, it occurs every 100 milliseconds, and it takes 50 milliseconds to complete. We have a printer routine, and it occurs every 500 milliseconds. This is all the information you would normally get. We have a background routine that we know in a 1 second period it uses 300 milliseconds to do what it has to do. So the question would be, what is the maximum amount of time allowed for the printer? Remember, these are ISRs. What is the maximum amount of time required for the printer? And if you wanted to extend the background routine for some new background, what is the maximum amount of time left to you to extend the background routine? Well, now we can fill in those with the rules we've been given. We know that the total amount of time for our interrupt service routines, the sum of these must not exceed the rate of arrival of the greatest. So if we've got a rate of arrival of the fastest is 100, that's faster than that. The sum of all the ISRs mustn't exceed that, so you have 50 milliseconds left to do your printer routine. Now in a 1 second period, we can calculate how much time is taken up by processing. The ADC routine occurs 10 times every second. So in each second, it's 10 times 50 milliseconds, 500 milliseconds ADC processing. The printer interrupt occurs twice a second because it occurs every 500 milliseconds. And we've calculated its maximum execution time is 50 milliseconds. So 100 milliseconds is devoted to the servicing the printer. The background routine we know requires already 300 milliseconds per second. So the already allocated time is 5, 6, 7, 8, 900 milliseconds has already been lost per second. So the new routine has a maximum amount of time of 100 milliseconds. That is an example of a typical sum you will have to do when developing real-time systems. So remember the rule. The total time taken to execute all interrupt routines must be greater than the rate of arrival of the fastest interrupt routine. Given that, you can then calculate over a fixed period of time how much processor time has been lost to the interrupts. This tells you how much is left for your background processing, and that can be interspersed between the interrupt routines. And that ends our discussion on interrupt. Hello, welcome to the section on operating systems. Now, before I move on, I was rooting through my desk and I found this wonderful antique, which is in fact a demonstration of an ADC. I thought I must show this to you because it breaks up the day, it's a lot of fun, and let's see things moving. So we'll bring it over to the scanner and we'll look at it in a little bit more detail, and of course the chance of it still working is nil. But it's an old moving coil meter like you get out of old science fiction films. Here we have a capacitor, charging capacitor, and this is a simulation of an ADC. What I have here, simple little 9-volt battery and a simple little twiddle pot potentiometer like a volume control on a hi-fi, and all this does is vary the voltage. And what I wanted to show you was an ADC, a dual slope ADC. So when I attach the voltage, it charges up and then it discharges. Now if I vary the input voltage, you will see that the rate of charging will vary. There is a very high voltage and then it discharges. Reduce the voltage, there's lower voltage. And notice the discharge rate is always the same. So the way that an ADC works, a dual slope ADC, is we apply our unknown voltage for a fixed period of time, 1, 2, 3, 4, and then we time how long it takes to discharge. Obviously the further it manages to charge up in those 4 seconds, the longer it will take to discharge. So here we go, 1, 2, 3, 4, and now we let it discharge. The higher the input voltage, the longer it takes to discharge. So there we have a simple demonstration of a dual slope ADC. We'll put the little antique away and we'll move on to something more interesting, or you may not think it's interesting, operating systems. The nice thing about operating systems, as far as real-time systems are concerned, is we don't really need to worry about them. The real hard work and the area where you should put the most of your revision in is into interrupts, because the vast majority of real-time systems do not use an operating system. They're actually based around parallel processes which are generated by these interrupt functions that come into existence momentarily, do what they want to do and go away. So that's the real hard work, is designing multi-processing in an asynchronous manner by handling lots of different interrupt sources and then how you move data between them. But we should also give some cursory look at operating systems in the traditional sense, because they still do play a role in some real-time systems. Now, the traditional multitasking, multi-user operating system is based on the concept of stack frames. Now, this is something that you may have studied elsewhere. It's not part of this module. I won't examine you on this. I'm just introducing the more complex end. Now, the way a stack frame works is that you have a real-time executive that is regularly interrupting. When it interrupts, it suspends the current active task. It's a very similar way to an interrupt routine. It just suspends it. It doesn't finish it, it suspends it. And it keeps a copy of where it was, its program counter, its memory usage, into a thing called a stack frame, a block of memory. So what happens is, if we consider what's happening in an operating system, we will have function 1, let's say, function 2, function 3. These tasks normally are running forever or running to completion. I mean, it's just like Windows. You start up, you click on an icon and it's running until it completes or until you switch it off. So it's like having 3 multitasks running. Now, how does the operating system arbitrate between them? Well, somewhere or other, there will be an RTI, a real-time interrupt, occurring at regular intervals, typically kilohertz, let's say. And what it does is that every time there is an interrupt, whichever is the active task is suspended, is put to sleep. And a copy is taken into a stack frame of all the registers and memory it was using. So associated with each function, there is a frame that belongs to the real-time interrupt. It suspends the operation of the current active task, keeps an image of what the processor was doing at the time it was suspended, and then it starts the next one off. So that now runs until that interrupt occurs. When this interrupt occurs, this task is suspended, the stack frame is created for function 2, and then function 3 is started. On the next interrupt, function 3 will be suspended, and the contents of the function 1 stack frame is restored, and we restart it. So what we're doing is we're time slicing. We have these functions. They're not designed to be chopped up. They are whole functions. They're either started and left to run forever, or they will have a natural completion, but they share the processor resources. These functions have no knowledge of each other. They're totally independent. But running in the background is this real-time interrupt that is switching them on and off in turn. And every time it suspends a task, it has to create a stack frame with the status of that processor in, so that when it is restarted, that information can be restored. It's like having an interrupt that's chopping up a function, stops it, takes a copy of where it was, goes off and does something else. And when it finally gets around them all, comes back to you, that's where it paused, it restores the stack frame, and it runs again. So you get individual time slots, time shared. That is lethal for a real-time system. Why? Because when a function is set off to run, it must be completed within a certain time frame. We know our ADC must be executed 100 times a second. We know the pulse width modulation must go out at regular intervals. We know things must happen within certain times. With this concept of the stack frame, we could keep on adding more and more functions, and what happens is you get less and less of the processor resources. So the system slows down. There's no guarantee of when any particular function will complete. Such an operating system should not be used in a real-time system. The only way you can do it is by overlaying on top of the operating system specific requirements that put certain functions have high priorities and they must have fixed periods of time. And that sort of operating system gets extremely complex. Forget it. Go back to something simpler. Things that are simple are much easier to manage and maintain. What is the simplest sort of operating system? Well, if we've got 3 functions, why don't we just call function 1, then we call function 2, and then we call function 3, and go back to the beginning. What's wrong with that? There's absolutely nothing wrong with this at all. So we could just say call function 1, call function 2, call function 3, or whatever our programming language is, and go back to the beginning. Alright, it may look trivial, but it is an operating system, because all it's doing is executing and scheduling 3 functions to run to completion. Why is it valid for us? Because I've given you the constraint. The constraint is, in real-time systems, your functions must run to completion. You can have a background function that fills in the gaps, and that can spread forever. But if you've got real-time functions, when they're scheduled to run, they must finish. So this structure, just going round and round the routines, is perfectly valid. And the vast majority of real-time systems, the operating system, is no more than a series of threaded codes calling subroutine 1, 2, 3, 4. You may get a series of logical decisions in it, so you can get some signals and flags to make it a bit cleverer. So what we can do is that we can have function 1, function 2, function 3, and then go back to the beginning. We could insert into here some simple logic that makes us jump past particular functions, or make us branch off and insert a new function and then return, but it's still the same basic concept. And all we've done, we've implemented very simply some means of suspending functions, i.e. by jumping around that we've suspended function 2, or momentarily bringing into life function 4. It's trivial, and you can write operating systems such as this without even thinking about it. Let's take the complexity a little bit further, because in practice, rather than letting things run around forever, usually they have to happen within a time slot. So the typical thing you end up with is to have function 1 followed by function 2 followed by function 3, and then wait. What are we waiting for? We're waiting for a real-time interrupt to say, right, 100 milliseconds has passed, and then go back to the beginning. This sort of structure also is a valid operating system, and again, there's a whole swathe of real-time systems out there that do just that. Things must happen in sequence, they must happen within certain time frames. There's no point going faster than that, so all you do is you say, do this, do this, do this, do this, now wait, look at the clock. And when the clock reaches the right time, do this, do this, do this, do this, stop. Do that, do this, do this, do this, do this. That is an operating system, and it's usually good enough for the job. So don't be frightened about operating systems. Usually they're very simple, far simpler than a lot of people are let on. All the difficulty for you has gone into the interrupt handling. That's where the complexity is. But the operating systems, they are very, very simple. Now what is this? This type of operating system I've described here, it actually even has a name. It's just a timed loop. Very simple. In a fixed time interval, we will always do that, that, that. And if there's time left over, you do nothing. Well, I suppose if you want to make that a bit cleverer, why not now implement a little background routine and let that fill up the time? And that way we can actually make use of all the spare time to do some slow housekeeping that you can suspend. So you can add a little bit more complexity. Split your task down into the real-time events, the things that must happen, and they will be scheduled to run. Any time left over, get back to the background routine, do some housekeeping, update a printer, do a log, service a keyboard, all the things that are slow and unimportant. But then when the real-time interrupt comes around again, schedule these things to run. And you can do it under interrupt control. Take my simple timed loop, and now we can turn this into a multiprocessor function. We can have a background routine, all our unimportant things, and that will run forever. But in the meantime, we will have a real-time interrupt occurring, say, once every 1 kilohertz or 100 hertz, and that directly executes function 1, function 2, function 3, and then returns from interrupt. Here we have a simple multitasking environment, the simplest operating system you can get. We have a real-time interrupt occurring at this interrupt rate. We're executing F1, F2, F3. Now remember, the total execution time of all these three functions must be faster than the rate of arrival of the interrupt. They've all got to be done in that time. And then we will return, every time this happens, we go to there, we return to the background. So here, what we are doing is allocating all the available time to our background routine, slow processing. So we've moved on now from something really trivial, very quickly, 3 functions, do 1, do 2, do 3. We've very easily moved on with a single interrupt to create a multitasking environment. We have here a background routine. It runs forever, but it is paused, it is suspended to run the fast real-time routines, function 1, function 2, function 3. And then, only if there is some time left over, will it go back to the background and do a little bit more of it. So we have here parallel processes, a real-time executive scheduling 3 functions to run, and all the spare time being given back to the background routine. Now that wasn't difficult, was it? So we moved on from a simple program loop to a multitasking environment with 3 scheduled routines running every real-time interrupt and a background routine that is suspended while those occur. That wasn't difficult, was it? Let's go on a little bit further. Now, what happens though if in this system we have these 3 functions? What if these have to execute at different time intervals? Now it gets a little bit more complicated. Now there are many solutions to this. I'm just going to give you one because it's very rare that I've had to implement anything more complex than the diagram you've just seen. But there was one system I worked on, and that was a robot lawnmower. And I'm not joking, it was a robot lawnmower. Its job was you put it down on the lawn, it went off to find the grass and it cut it for you. It was a rich man's plaything. And it was a very complex robot because it had to take account of lots of things. Has it got the grass? Is it going to fall down a ditch? Is it going to run over a child that's in the way? Is it going to kick a football that's been left out? Is it battery flat? It was a multitasking, multifunction system that required quite a complex operating system. But it still had the constraint that all of the functions had to be completed within a specific time frame. So that meant that we could develop a scheduled real-time interrupt without using a multitasking operating system. And I'm going to explain that structure to you bit at a time. How can we first achieve it? Well, firstly, we need to have some memory location that tells us some information about the operating system, the functions themselves. So the first thing we're going to do is we'll create a little array. This is just in data memory, and we have associated with each specific function, we have a repetition variable. Now we actually, to get this thing going, I had a 100 Hertz interrupt, a real-time interrupt. And all of these functions that were available were scheduled to run within units of 100 Hertz. So if I wanted function 1 to run every 100 Hertz, I put the 1 in there. If I wanted function 2 to run every 300 milliseconds, I put a 3 in there. If I wanted this to happen every 500 milliseconds, I put a 5 in there. So what we have is an interrupt that is happening every 100 milliseconds. That's 200, 300, and so on. Click, 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 click. And these, the repetition count, was in units of 100 milliseconds. So the basic table looked like this. For each function, we said, right, function 1 happens every 100 milliseconds, function 2 every 300, function 3 every 500 milliseconds, and we have a regular 100 millisecond interrupt occurring to signal those events. Now, the main thing we did is that we did not try and execute the routines inside the interrupt routine itself. What we did is we signaled that they were ready to run elsewhere. So we built up a very simple system. And what happened with it? Go to our repetition count. This was a constant. The actual repetition rate was a constant. Every time the 100 millisecond event occurred, the count fields were incremented. This happened inside the ISR. So we had a real-time interrupt, and it did the incrementing of the count. So if that was 0, that would go to 1. If that was 0, that would go to 1, and then that would go to 1. Next time round, that would go to 2, that would go to 3. Now what was happening in the background routine is there was a scheduler, and that scheduler was looking to see whether the count matched the repetition rate. If that matched that, then it would run the function. So to make that easier to handle, in an array, we extended the array to have a repetition, a count, and a flag, a signal. Now the repetition rate again would be 1, 3 and 5 for 100 milliseconds, 300 and 500. On the first interrupt, that would go to a 1, because that was a 1 and that was a 1, that was signalled true. That would go to a 1 and that would go to a 1. On the next interrupt, then that would go to a 2 and that would go to a 2. Only when that equals that would that be signalled to be true. Now this in fact was our semaphore. The background routine, every time it had finished doing what it was wanted to do, it would go and look at this table and say, right, are any functions ready to run? And if it saw a signal true, then it would run function 1 and it would reset the count back to 0. So this was used as, we used an array as the semaphore. The repetition rate tells us how quickly the thing needs to actually run. So this was a constant. The interrupt routine incremented the count fields. When the repetition rate equals the count fields, it was signaled ready to run. The background routine continually scans the ready field. If it sees a function is ready to run, it actually runs it just simply by calling it. It switches the ready field to 0 and resets the counter back to 0. So that means that we have the ability to schedule a function to run, one to run every 100 milliseconds, this ran every 300, this ran every 500. Because what would be happening in time, if you looked at the count fields, we would go 1, 3, 5, we go 1, 1, 1 would be at time slot 1. That would be signaled to run, so it would happen every 100 milliseconds. Next time round, we'd get 1, 2, 2, so that's signaled to run again every 100 milliseconds, but not these. Then we'd get 1, 3, 3. That runs and that runs, but not that one. That one will not run until it equals 5. So every time we come into the interrupt routine, we increment the count field. When the counter equals the repetition rate, the function is signaled to run. The background routine, its job is it just scans the ready field. That's all, that's its signal. Whenever any of these are signaled to run, it just calls the relevant function in a table. So it says, if function 1 ready is true, execute function 1. If function 2 ready is true, execute function 2. Very, very simple bit of code. And so by a simple mechanism such as this, we're able to schedule 3 different functions to run at 3 different time intervals. And all these time intervals are units of 100 milliseconds. Then we took the thing further. So we now have our mechanism. We have a real-time interrupt executing every 100 milliseconds. It's checking the repetition rates, it's incrementing the counters. If there's an equality, it's setting a signal that a function is now ready to be scheduled to run. The background routine has to scan that all the time and execute it. The standard constraint of interrupts is still true. The total execution time of all of our functions must be greater than the rate of arrival of the fastest, otherwise the operating system will not operate. In fact, what happens is it will gracefully decay, because functions will be signalled to run when they still haven't been executed. We then added another level of complexity, because we found that some functions would require other functions to run. We needed the mechanism in our operating system to kill off functions and to bring others to life. And that was achieved by another very simple addition to the array. We added another field, which was the active field. So we kept our repetition rate the same, 1, 3, and 5. Remember, these are constants, so this is the actual repetition rate. The counter field is being managed by the ISR. The interrupt service routine is busy incrementing the contents of this, again, 1, 1, 1, 1, 2, 2, etc., etc. When that equals that, we're setting signals. But in addition, we have this other field which tells us whether or not the whole field was active. So if we were to put a 0 into there, even if it's ready to run, because that has been declared inactive, it kills off the function. Now, similarly, let's assume this one has reached 5. If that equals 5, that's ready. And if it's active, only then did our scheduler run function 3. So we have the ability to set different execution times. This is the field used by the ISR. Functions are signaled to be ready, and we have an activity flag which allows us to kill off. In this case, we killed off function 1, but we left function 3 alive. Now, we didn't have time to go into the lawnmower in great detail, but in fact it was an expert system, and the way it worked is that it brought functions to life and it killed them off. It brought rules to life and it killed rules off. That's why we needed this complexity. It was adaptive. It was an adaptive control system. When it discovered a rule that was working, it would make it active. If it liked it, in fact, you could go back to this array and you could make it execute faster. How? Well, you have the ability here. The repetition count field tells us how often it should run. Well, if you're winning with a particular function, all you have to do is to decrease the repetition count to make it run faster. All of this array is available for us to use. It's all in RAM. It's a whole load, as long as you use the rules related to semaphores and signaling correctly. Here we have, and let's have a neater one to look at. Here's the basic array. Repetition rate, how quickly. There is the ISR doing the counting. These are the signals to say they're ready to run, they've been scheduled, and here we have the ability to kill them off or to make them globally alive. A very simple operating system. However, it is possible for more than one function to become active at the same time. So the final part of our very simple multitasking operating system was to implement a priority structure. The way we did that was, again, another array, element in the array was a priority number. So we had in here our repetition, 1, 3, 5. So run function 1 every 100 milliseconds. And we had the ability to make it true or not true. So we could bring them to life or kill them off as we wished under program control. These two fields are used by the interrupt service routine. If the function is active, then you increment the count. If the count equals the rate, then you would signal the function to run. Our scheduler, which is in fact running in our background routine, its job is to look at that field. If any function is active, then it should be run, but we can give it a priority number. Which ones are most important? Well, if we say that's true and that's true, we give that priority 1 and that priority level 2. Our scheduler can first look at all the high priority functions and execute those, and then if there's none of those pending, then it tries the next level of priorities. And we actually implemented 8 levels of priorities. So I'll leave you with this final picture. It was a very simple structure. It's a true multitasking operating system. It works only because it obeys the rule that any function that is executed must be completed, and all the functions must have an execution time that is faster than the rate of arrival of the fastest routine. Given those constraints, which are standard for real-time systems, you can implement a multitasking operating system using a very, very simple array structure such as this. Repetition count, the ISR comes in, increments a counter. When there is an equality between the repetition count and the current counter, a function is signaled to run. And if it is signaled to run and it is active, the scheduler, all the scheduler has to do is just call function 1 and then reset these variables back to 0. you can implement a priority function very easily in a priority field. Now all I need you to know for this module is something like that. It's the most complex operating system you're going to get. The chances of you getting involved in true multitasking with stack frames, suspending tasks is very unlikely. If you do, then don't try and write it yourself. You can buy off-the-shelf real-time kernels which will do all this for you. You don't develop your own operating system anymore, you buy them. But the chances that you will need anything as complex as a true stack frames, task suspending multi-operating system is minimal. The vast majority of things you do will simply be a simple timed loop going round and round and round at fixed time intervals. If it's more complex than that, then perhaps you want to look at a simple scheduler arrangement. But the most complex scheduler you're ever going to come across is something as simple as this. This was just a byte array. The whole thing was done in about, what's this, 1, 2, 3, 4, 5, we had 8 tasks, 40 bytes of memory, data memory, were used to implement the whole operating system. And all the scheduler was, it just ran down it. It was just an if this, then else. A very simple bit of logic, just ran down the task list and ran the function that needed to run. Very, very simple, very easy. Don't be afraid of operating systems. Put your thoughts and energy into thinking more about interrupts.